Here's problem 2926. A proton is accelerated from rest through a potential difference of 150 volts. It then enters a region of uniform magnetic field and moves in a circular path of radius 12 centimeters. What is the magnitude of the magnetic field in this region? Well, if we accelerate the proton through a potential difference, its change in potential energy will equal the charge times that change in potential. And in this case, that's going to be the charge on a proton, 1.6 times 10 to the minus 19 coulombs, times this 150 volts. And that's going to equal 2.4 times 10 to the minus 17 joules. Our change in kinetic energy will equal our change in potential energy, which would be equal to this 2.4 times 10 to the minus 17 joules. And since we started from rest, that means our final kinetic energy will have this value as well. So our final kinetic energy is 1/2 mass times velocity squared. So our velocity will be equal to 2 times the kinetic energy divided by the mass, square root. That's 2 times our final kinetic energy, 2.4 times 10 to the minus 17 joules, or the mass of a proton, 1.67 times 10 to the minus 27. All this square root, and this is equal to 1.69 times 10 to the 5 meters per second. So that's the velocity of our proton when it enters the magnetic field. With that velocity, it will subtend through a radius equal to mass times velocity over charge times magnetic field. We know the velocity, we know the radius. We can solve this for the magnetic field. So that's going to equal mass times velocity over charge times radius. And this is going to equal the mass of a proton, 1.67 times 10 to the minus 27, times the velocity we just calculated, 1.69 times 10 to the 5, over the charge of a proton, 1.6 times 10 to the minus 19 coulombs, and the radius is 12 centimeters, so it'll be 0.12 meters for the radius, and this is equal to 0.0147 Tesla. Everything's SI units, so we come up with 0.0147 Tesla, which we could write as 14.7 millitesla. So that is the magnitude of our magnetic field, 14.7 millitesla.